Okay, so the success criteria for today's lesson are up there. So number one, you can explain the difference between simplifying and solving. It's going to be the first question I ask. And the second one is going to be able to perform binomial expansions. Now, this is, I'll take a question second, Mitch. This is sort of coming off the back of your previous unit in core maths. Okay, so it takes your core maths work and then extends it further. I know that I said to quite a few people last week, oh, you better be careful, algebraic fractions is coming up. It is coming up, but term 3, I just made a mistake. I was looking at my sequence of units and got all excited about seeing algebraic fractions, but they're actually further on in the year. Okay, Mitch, question? Not this bit here. I'll try it, at least for the first part of the year, give you explicit instructions as to this should go in your summary book, okay? So good question. Anything else? Okay, so that's where we're headed. So the first question I want to ask you is that then, and I just want a bit of student feedback. And what's the difference between, I'll tell you what's the same about them first of all. They're simplifying and there is solving. The thing that's similar, the same about them, is that they both start with S. Other than that, they are different words in mathematics and they have different meanings behind them. What are they? Who knows? Have a discussion very quickly in your table group, and then I'll get answers from the front. You want to put your finger down with it? Okay.
Yeah, so simplifying is making it more basic. Solving is getting an answer. Yeah. Nice. Is it like, so if there's like a 9 squared simplifying it, if you were simplifying squares, you keep it down to the square, and solving it's like the actual answer?
Yeah, sort of. That's getting there. What you said about 9 squared becoming 81 is simplifying. But how's it different from solving though? This is a very quiet table group.
Yeah.
You got anything at all?
Oh, no.
Something about consolidating go Riley. I don't know if that works. That's all right. It'll come out in the wash. You got anything?
Yeah. Simplifying is turning it into a shorter equation, and solving it is turning it into a number.
Yeah, that's not too bad. Although I wouldn't say it's turning into a shorter equation.
Yeah.
We'll pull that out in a second. You guys got anything?
Yes.
What have you got?
Simplifying
Simplifying isn't solving.
No, well,
Elephants aren't solving either. That doesn't really tell us what the differences are. Elephants are grey and equations are not.
Simplifying is where you make the equation easier to understand and smaller.
Okay, we'll build on that, but that's a good start. And equations?
Solving is finding the answer. The very end answer.
Finding the answer. Okay.
So that it doesn't have a plus or minus times.
Okay, thanks. That's not too bad. Okay, we'll just draw that back to the front again. Okay, that was a good little discussion. I went around to each table group, so we might not bring it back. We might not get people to call it out to the front, but more or less, the basic idea was okay there. People talked about simplifying as about moving from something that's more complicated to more basic or more simple. That was okay, and then solving was about finding an answer was the most common thing I heard around the table groups. That's okay. I guess the trick with solving though is that you need to have this thing in the in your problem, an equal sign. So solving is about finding an answer, or to be a little bit more precise, it's about finding values for variables such that the equation is true. So if I have something like 3x plus 2 is equal to 14, then what I'm trying to do is I'm trying to work out what is the value of x such that the left-hand side evaluates to the same answer, or the same value, I should say, as the right-hand side. Now, the right-hand side is nice and simple. It's 14. So I'm really asking myself, what do I multiply 3 by and then add 2 to the result to get 14? And the answer is, of course, 7.1. No, it's 4. So x is equal to 4. So solving is finding an answer. It's finding that x is 4. But finding an answer is even saying that is just a little bit of a rough way of saying exactly what's going on. What exactly is happening is we have an equation. There's an equal sign in it. Now, I know in my class we did this, but I'm sure you did in other classes as well. When we have an equal sign, it's like a balance scales. And we have some weights on the left-hand side, and we have some weights on the right-hand side. And when we have an equation, it's like the left-hand side of those scale is the same weight or same value as the right-hand side. And when we solve an equation, it's all about finding the specific value of the unknown, in this case x, which makes that true. How could this be balanced? And the answer is this can only be balanced if x is equal to 4. Okay, so that's what finding the answer means if we unpack that. Any questions about that? We are not doing equation solving right now. It's important for the context of what we are doing though. So that's equation solving, and don't ever use the word equation unless there's an equal sign involved somewhere. The more general term we use to describe something that we, for example, might be simplifying is also starts with E, just to be confusing, but it's expression, okay? So if I have an expression, and I'll just give you an example here, 3x squared plus 4x squared plus 2, and I ask you to simplify it, I am saying that you need to use a series of methods and techniques to take that expression, which is of a number of parts, and reduce it to an expression of fewer parts. So, for example, 3x squared plus 4x squared plus 2 is just 7x squared plus 2. And I can't simplify that further, which means that without knowing the value of x, I have no way of reducing that expression to something that's even simpler. The most simplest expression would be a single number. Whether it's 5, negative 17, or pi, it's a single number, identifiable number. Okay? Now, what did I do just then? Can anyone name the technique I just used to simplify that expression? Max? Oh, perfect, great. So collecting, which means adding and subtracting terms. Terms are variables that are multiplied together with a number, usually in front, but it doesn't have to be. That number is called the... I actually heard some right answers there, which is really good. Aaron? Good, is the coefficient. There is only one coefficient, and oops, I should actually do it on here so people can see on the video. So there's only one coefficient, 3. This is not a coefficient because the coefficient is really repeated addition, x squared plus x squared plus x squared, whereas this 2 here is an index, it's repeated multiplication, x times x. And so we have terms, we have coefficients, and we have collecting like terms, which means if the terms have exactly the same variables with exactly the same powers, or can be rewritten so it looks like that, then the coefficients are added or subtracted together. So a lot to unpack there, but that's a process, that's a technique of simplifying an expression. Okay, does anyone have any questions about that? So typically, this idea of simplification occurs because what we want to do is we want to solve equations, yeah? So I want you to see this part of the unit as developing some techniques to manipulate algebraic expressions so that as you grow in your mathematical journey, you can use those techniques in order to solve equations. That's what it's all about. So it's going to seem like as if, well, what's the point in it? And of course, I'm not talking about you need to know how to expand to binomial expressions because otherwise you can't order your meal at McDonald's. That's not the point of what we're doing here. Just think of it instead as if you can learn these techniques, it opens up your ability to solve harder mathematics and mathematical equations, and to be able to do higher order science subjects like not just mathematics, but also physics, chemistry, biology, and all those engineering, all of those sorts of things that will require a higher order of mathematics. So that's the buy-in for you guys. Jamie.
Back on the page when you said it was 3x is 3 plus x, like 3 times.
Sorry, no, I did not say that, but I apologize if I was confusing. All I'm saying is that the coefficient is the big number, really. It's the main thing you need to know. All I was saying is that 3x squared really means x squared plus x squared plus x squared. That's all I was saying. Yeah. And then the squared bit is repeated. So it's repeated addition. You know that. Multiplication is a repeated addition. Like 10 times 4 is 4 plus 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 4. And then indices are repeated multiplication. So x to the power of 10 is x times 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 x. Okay, so indices, repeated multiplication, and multiplication is repeated addition, which I'm pretty sure makes indices actually repeated addition. But that's for another day. Okay, so the more techniques we have to simplify expressions, the more sophisticated kind of stuff we can solve when it comes to further mathematics. So we talked about one just then. So if I just looked at some techniques, I'll continue writing in red, why not? No, I won't, because it's a bit hard to see sometimes. So techniques, we just talked about collecting like terms and what that means. What other techniques do you know for simplifying? Yeah, but Mitch, what is that though? No, it's not really collecting like terms, although you do end up using collecting like terms after using the box method. Yeah, expansions. You said the other one too, which is good. Factorizing. And sometimes students sort of say, do I factorize this at the end? Is that more simpler, or is it expansions more simpler? And the answer is pretty dodgy. The answer is depends what you do next. So by itself, you can't really tell whether factorizing or expanding is worth it. But if you are, for example, solving an equation, you don't need to know this at all, right? But if I had an equation like x squared plus 3x minus 4, then that would factorize to x plus 4x minus 1. And then if I said that was equal to 0, then I can use this law called the null factor law, which basically says that if I've got two things multiplied together and they equal 0, then one of them must be 0. And then I can conclude, therefore, x equals -4 and x is equal to 1. So I can do all that. And so the natural simplification step is to take this complicated expression here and then simplify it to a factor form so that I can use the equation, the null factor law, to solve the equation. So it's, I'm going to do this so I don't upset people. There, gone. Don't have to think about it again. Okay, so we've got collecting like terms, expansions, factorizations, and within those particular kinds of techniques, there are other techniques as well. So for example, for expansions and factorizing, you learn how to recognize and expand a perfect square, recognize and expand a difference of two squares. And later on in your maths, sum and difference of cubes. And there's quite a lot of techniques to unpack, but they're the three key ones. So we're focusing today on expansions, and we'll do that for the next couple of lessons. And then after that, we are going to spend some time looking at factorization. And again, we just keep on adding techniques, or if you think about your algebra toolkit, we're just adding more tools into your toolkit. So the fuller your bag is, the more complex the kind of problems are that you can solve. Okay, so I'm going to write a problem up on the board, and in your workbook, so it doesn't need to be a summary book, I want you to solve it. You can talk about it. You can try and work it out with a friend. It's up to you. I'm just going to give you a couple of minutes to try and solve it. So here goes. Yes. Okay, so what I'm going to do is I'm going to go through the solution. Some people got the right answer. I didn't see everybody's. A lot of people didn't. And that means you have failed to get it right. Thank you, Mitch. There is nothing wrong with the F word. Remember that, because if you fail to get it right, if you now identify why you failed to get it right, you've got your next step to success, right? Was it that you didn't know how to expand 3 outside of x plus 1? Was it that you couldn't expand the middle bit, which is what we call a binomial expansion? Or is it that you failed to collect the like terms correctly? If you don't get the right answer, that's something for you to go, right, that's a diagnostic tool for me to say, this is what I need to do next. So I think that's all good. the only bad thing is when you sit there and say, I failed to get it right, so I suck at math, so I better go find something else to do. No, you just move on with it. You just move onwards and upwards. So I'm going to show you a few different techniques as I go along, but this is, it's not that hard a problem, but there's a few techniques in them. If you don't know the techniques, then that's when you can come undone. So first of all, I'll just put my equal sign over here, and then I'm going to continue to put my equal signs underneath each other. I'll be checking your communication for that. So if you're used to just putting equal signs randomly, 3 on one line or whatever else, today's the day you stop. All right. So I'm going to do some expansions first. The first one is simply using what we call the distributive law. And the distributive law simply says if I have something outside the bracket and I have a couple of things inside the bracket, I multiply each thing inside the bracket by what's outside. So I go 3 times x is 3x, and 3 times 1 is 3. Right so far? Okay, now the next thing, I might just zoom out because that's a bit too scary. There we go. The next thing is multiplying x plus 2 times x minus 1. Now, I know that you've done this in 9 maths, so core maths. So I'm going to, in slide 7 there, just show you very quickly to remind you how to do it. So we've got the box method. Now, would you like to know how long I've been using the box method? I don't care. I'm going to tell you anyway. That was a trick question. I've been using the box method for as long as I've been at Friends and not a moment longer. I first learned it when I got here. So it's not really my natural way of working. And I know it's a little bit cumbersome because it takes up room to do, it's quite big. Can I just say a couple of things to you? First of all, I find it, I wouldn't always use the box method. If it's a simple expansion, I just do it in my head, and I'm okay if you do that too. There are other methods you can use, like the FOIL method or the chicken beak method, and I'm going to show you the chicken beak method in a second. But I can tell you this for real. This is the one thing I found with the box method. The box method is absolutely brilliant for solving higher order problems. Even though it might look a little bit, I'm drawing pictures, that can't be more sophisticated. But when you get to something called polynomial division in grade 10 Maths Extended, polynomial division, the only place I've seen it actually make a lot of sense, the process of doing it, is when you do a form of reverse box method. So I don't care whether you use it or not. I care if you don't know how to use it because it's important for next year. So if you're sitting there saying, but I don't like it, I don't want to use it, that's okay as long as you can still use it under pressure if you need to. And if the answer is no, practice until you can. All right, so here's the box method. So we just, it's like we're dividing an area up. X times x is x squared. Negative 1 times 2 is negative 2. X times negative 1 is negative x. 2 times x is 2x. And then I read across the diagonal there to add them together to get positive x. And so my expansion becomes x squared plus x minus 2. Are we good with that? Shall I show you the chicken beak method? Won't take long. Oops, it'd be helpful if I actually wrote it down correctly though. Is that right? I flipped them around, but it's the same deal. So the chicken beak method basically says multiply everything in the first set of brackets by everything in the second set of brackets. So I go x times x and x times 2, and then I go minus 1 times x and minus 1 times 2. And they kind of look like a chicken beak, like a bird beak kind of thing. Okay, that's the top of it, and that's the bottom bit. And if I was a really good drawer, I'd turn it into a chicken. But if I did that, it would be a very awkward moment for us all. So I won't do that. But that's the chicken beak method. So if I follow the first line through, I get x times x is x squared. I follow the next line through, and I get x times 2 is 2x. And then underneath, minus 1 times x is minus x, and minus 1 times 2 is minus 2. And that gives me x squared plus x minus 2, which is the same as the other side. So both methods are perfectly valid. But again, if you don't know how to use the box method, please do. Now, this is the first alert for you guys. This is where I reckon a lot of you went wrong when I was going around. And that is, you need to do this, minus x squared plus x minus 2 plus 3. Notice how I've got brackets around the expression I just expanded, but the negative is still outside there with those brackets. That has a real effect. Now, I'm not putting that subtraction and the brackets in there because I want to, I wouldn't do it myself, but I'm just showing you students just so you know what to do. 20 years on after my teaching degree, I will still put brackets in when I get a subtraction, because I know, particularly under pressure, it's really easy to get your negative number work stuffed up. So I always, whenever I have a subtraction involved, I always take an extra step to make sure I'm not stuffing up. Because then when I have a negative outside the bracket, the negative changes the sign of everything inside it, because effectively I'm distributing a -1. And -1 times anything is just the reverse sign. So -1 times x squared is negative x squared, -1 times x is negative x, and -1 times -2 is positive 2, like so. Okay? So, that was the long-winded way of saying it. The short-winded way of saying it is saying when you have a negative outside the brackets, change the sign of everything inside. Okay, so pluses become minuses, minuses become pluses. Okay, next is then to collect like terms. So I'm just going from left to right to start with. And it's not a bad thing to get a different colored pen or just a little tick and just go along. So 3x. Now I can't subtract x squared from that because they're different powers, but I've got a negative x there. So that's 2x. And then I've got a 3 and then another 3, so that's 6. Oh, and a 2. I missed that. So that's 8. And then that just leaves me with a negative x squared left over all by its lonesome. So the expansion is 2x plus 8 minus x squared. Now, that's a bit of an untidy way of keeping it. So there's no real hard and fast rule, but generally speaking, when you end up with more than three terms or more, typically we'll write those terms from highest power to lowest power. So the gold standard answer is negative x squared plus 2x plus 8. So notice that the negative next to the x squared travels with it. Okay, so the sign next to the power travels with it, and the 2x at the front there, it was positive 2x, so it becomes a plus 2x at the end there. Okay, does anyone have any questions about that? If you think it's just you, I'm happy to just come to you when you need me. But if you think it might be a question that everyone might appreciate hearing, now's the time to ask. Miranda. Okay, thanks for that question. So what I was saying, I probably shouldn't have used the big dashed line like that. But what I'm saying is that when we use the box method, we collect like terms by looking across the diagonal. So there is no diagonal here and here. So that's just x squared minus x plus 2x. Adding up, the diagonals will always have the like terms. So minus x plus 2x is x, and then the minus 2 doesn't have any other diagonals, so it's just minus 2. So we always add along the diagonals. Nice question, Miranda. And that reminds me to say something which is a bit counterintuitive to 9 Maths core, really. People who have had me for a teacher before know that I'm pretty strong on communication and think it's critical that you explain your solutions really clearly. And in a way, writing minus x plus 2x underneath, which is what I think you were saying, and then simplifying from here, would seem to be like a good communication step. However, you're Maths Extended students, and we expect you to be dealing with higher order mathematics, and as such, the default position for what you can expect the reader to know has also changed. So I would expect the reader to be able to see how you got plus x here by reading across by looking at the box method. So in fact, by copying it all down, it almost sends me a signal that perhaps you don't get that the diagonals will always be the like terms. So it's a sense of over communicating in Maths Extended, and thus demonstrating that maybe you're not quite sure what's going on. Now I will signal very clearly where I expect you to take shortcuts. You can see very clearly for this one here that that I said do not take a shortcut when it comes to negative work here. Okay, that's very clear for an extended student or for an old teacher. Don't take shortcuts with subtractions because it can come and bite you on the bum later. okay? But there are other things that you can and should shortcut, and I will signpost them very clearly. Anyone got any questions about that? Okay, what's the time? All right, cool. Just taking a bit longer than I meant to. So I've just got a very quick example for you to try, and then we can spend the rest of the time in bookwork. I'm going to give you a new expansion I don't think you would have come across in 9 core. Probably worth putting into your summary book. So I'm just going to let you get yourselves ready with your summary book. Okay, so unit title, algebraic techniques, subheading there, expansions. And so I'm going to just go through some examples of expansions, just one for today. So here's an example. What happens if I gave you a binomial like x plus 1? Can you see why a binomial is called a binomial? Because there's 2. And we multiply it by a trinomial, which has there we go. This example is from the textbook, by the way. It's from exercise 8A, question 12A. So we've got x plus 1 times x squared plus x plus 1, and we have to expand that. Now, you can use the chicken beak method for this. You end up with basically a mutant chicken with lots of beaks, but you can still do it. Or you can use the box method. So I'm going to use the box method just so you get a feel for it, because that is the official Friends approved way of doing it. So in this case, because I've got a trinomial, rather than adding dividing into 4 pieces, I'm going to divide it into 6 like so. So I've got x squared plus x. I always put the signs in just to make sure I know what I'm doing. Plus 1, and I've got x plus 1 here on the side like so. And now I'll fill in those boxes. I'll do it in blue so you can sort of see it. So x times x squared is x cubed. I hope that's okay. I could tell, I had a look at your 9 core stuff and they said you'd done some index work, so I'm hoping that's okay. We've got x to the power of 1 times x to the power of 2. 1 and 2 is 3. And then I'll just keep on going crossways, I think. And then we've got x squared, and we've got positive x. Then we've got a positive x squared and a positive x, and 1 times 1 is 2. Says a lot of people, but it's 1. 1 times 1 is 1. So that's the box method done. And I won't draw this time because it was a bit confusing, but can you see that a natural consequence of using the box method is that the diagonals are always like terms? So I've got 1x cubed, I've got 2x squared, 2 x's, and a 1 there. That's nice, isn't it? So reading across the diagonals, and it's kind of critical that you sort of get that. So I've got my final line as being equals x cubed plus 2x squared. Just reading along the diagonals, x and x is 2x, and I've got a plus 1 at the end, and that's the an expansion. So that's a binomial times a trinomial. Okay, there are 20 minutes left in this lesson, about 15 minutes left in this lesson. I'm going to write on the board what you need to do. You're going to start on page 491 in the new textbook, not too sure what it is in the old one, and it's exercise 8A, and I've got a couple of questions for you to try. No, sorry, it's the regular core maths class, maths textbook. What I might do is, if you can write the questions down, I'll project it up onto the screen, because it's going to be, by the time you get there and back, the time will be gone. So it's exercise 8A, for those that have it. Sorry, I should have put something on Google Classroom to bring it from now on. Exercise 8A, page 491, straight into the deep end. You're doing question 12 and question 13, and if you finish those in 10 minutes, I'll have something else for you to do. Write them down quickly, and then I'll fire up my I don't even know, I've got my textbook on me. I'll try anyway.